All right, thank you. Good afternoon, everyone. Let me first thank the organizers for giving me this opportunity to present our technology on InGaN microLEDs. I'm Mikael, come from Hexagem. We're a small startup in Sweden. It's a spin-out from Lund University, and Professor Lars Samuelsson is the main founder, and he pioneered this technology. Outline of my talk, brief introduction. I'll try to keep this brief. Then like to go into motivate why we have chosen to work with this InGaN platelet LED technology. Talk about the material quality of our platelets, a little bit simple device processing, and then at the end show you the recent device performance we have managed to get. And then hopefully there's time for some conclusion. All right, so microLEDs have a lot of potential advantages: ultra high brightness, high contrast, fast switching, stable materials, long lifetimes, higher operating temperatures than OLEDs, for instance. Of course, these advantages also comes with challenges, and the two we are mainly focused on with our technology is the loss of efficiency as you scale down the LEDs below, in particular below 10 microns or so. It's typically the case for all colors. Red is the most difficult ones. And then the issue of wafer bow when you go to large wafers. So the reason why, in particular for red, you have lower material quality is the lattice mismatch between GaN and the indium gallium nitride quantum wells. And of course, the higher indium you have to reach red, the more the problem is. You create dislocations and other defects. Then in planar technologies, to make your LEDs, you use plasma processing, which induces damage surfaces, but also in the material. And that becomes worse as you scale it down when the surface to volume ratio increases. In planar materials, when you grow buffers, you need rather thick buffers to get the material quality up. And that, of course, again, it introduces strain between silicon sapphire and the GaN buffers and creates dislocations. But also the thermal expansion mismatch to the wafers causes wafer bow and can result in low yield in follow-on processes. So it's mainly the material quality and the fact that we can get around wafer bow issues with our technology that I will talk about today. So our approach is a bottom-up technology. It's non-planar. We are still using gallium nitride buffers on silicon or sapphire. The quality doesn't need to be great. It can be thin layers, high dislocation density. It's all fine. We put a growth mask on, typically silicon nitride, and then we pattern small openings in this growth mask down to the gallium nitride buffer. And then using conventional 3-nitride MOCVD, we grow indium gallium nitride selectively in these openings. So we create, as you see in the middle here, these InGaN platelets. So they're basically truncated pyramids. And thanks to the small openings, 100 to 200 nanometer of the growth mask, any dislocations in the buffer should not penetrate these holes. So we'd filter the dislocations. So the platelets are dislocation-free. We have also a very small area between the InGaN platelet and the GaN buffer, so you can have very efficient strain relaxation. So we grow directly 15% InGaN platelet material, barrier material for the red LEDs. So, oops, sorry, wrong button. So on these truncated pyramids, we grow the full LED structure. So each individual platelet is a fully working LED. The difference between the colors is, of course, the quantum well. So red, blue, or green we can do in the same material system. There's also no need for plasma processing. So out of the epi, we limit the growth, so we don't grow these platelets together to form a film. They are separated from out of the epi. And since we don't form the closed film, we don't add any extra strain, so we don't add to any bow issues. So whatever bow you have in the beginning, the GaN buffer, this is what you have after the epi growth.